For the aldol reaction, we will first begin with looking at the mechanism of the aldol condensation and reactions. Now, as the prerequisite for this reaction would be, it is the presence of two carbonyl structures in your starting materials. For this particular chemical reaction, you will have to remember your acid-base reactions. Think about it. If you have to abstract out a proton and you have a base, where are your acidic hydrogens on this structure? On this structure, your acidic hydrogens are right here. This is the carbonyl carbon. The first carbon is your alpha carbon. Because the substituents are different on these, I'm just labeling them as alpha and alpha prime. If the base abstracts this hydrogen, what kind of a intermediate will you get? You will get something like this. But if your base abstracts this hydrogen, then you will get an intermediate like this. Just by looking at these two, you know which is the more stable intermediate. So coming back, based on induction, the alpha carbons have the most acidic hydrogens. And this is what the base is going to abstract out. So this is the first step, the acid-base reaction that we are going to see. The base abstracts out the hydrogen from the alpha carbon. So the alpha hydrogen is abstracted out and an enolate is generated. So the ene word comes from the alkene and oate comes from the word the ester. Because I wanted to see this, there will be a resonance available here. So this is going to work as your nucleophile, not at the oxygen level, but at the carbon atom. And so this carbon, a negatively charged carbon, is your nucleophilic site of your aldol. So the generation of a nucleophile is the first step in this mechanism. The next part is the nucleophilic addition. So generation and then the addition. The nucleophile attacks the carbonyl. Because this alpha carbon does not have any hydrogens, we will not have any competitions of other nucleophiles being generated. So this is the only nucleophile that will be created in this particular reaction. And you are going to get a mechanistic arrow like this. Once this addition happens, the O negative generated can abstract out a proton from neighboring water molecule so that it becomes a clear and neutral molecule. So there are basically two steps involved. First is the acid base, second is the nucleophilic addition, and you can say third will be your protonation of the oxygen. At this point, I want you to see this is known as the aldol reaction. You have the carbonyl, you have the alcohol, a beta hydroxy ketone. A beta hydroxy ketone is 1, 2, or alpha, beta. So on the beta side of this carbonyl, we have a hydroxy group. Because both of these sides are substituted or have an alkyl group, we know it as a ketone. So when you have an aldol reaction product, it will be a beta hydroxy ketone. So what is the difference between an aldol reaction and the aldol condensation? When you have aldol condensation, then we have a dehydration. So in presence of a strong base, like sodium hydroxide, the carbonyls alpha carbon, if there is a hydrogen present here, will be abstracted out because this hydrogen is still acidic, more acidic. And then the base will abstract out this particular hydrogen and formation of your double bond will occur. But before all of this occurs, you need to get a good leaving group, which is a bad leaving group. So what is happening here beforehand is when you grab a proton from here, you will generate a good leaving group. Meanwhile, your base is abstracting out the alpha hydrogen. And this helps to our elimination reaction. So now earlier you had an alpha beta beta hydroxy, but that beta hydroxy is now missing. What you have is a condensed structure. We lost the water molecule, and so it is now known as an aldol condensation product. Alpha beta unsaturated. Alpha beta unsaturated product. So if you paid attention, one part of your ketone has now been substituted. So one of the parts of your experiment is to add in portions. Why do we add in portions? So that one of the parts, one of the sides of the ketone will get substituted. If you add all of your materials at once, you will get random mixing. Some of them will be mono substituted, some of them will be di substituted. So you will get a mixture of the products instead of getting just the di substituted product, which we eventually desire. And so once our one side has been substituted, we will go and abstract out the other sides or the other alpha carbons, hydrogens also. You will generate your nucleophile. You will then attack this nucleophile to your benzaldehyde or whatever aldehyde you have. And another protonation occurs. One more protonation will generate your good leaving group, water. And eventually, we will get our dye substituted product. So a few things to note at this point. We have used two equivalents of our aldehyde and one equivalent of our ketone. Just by looking at it, we know who's going to be our limiting reagent. Another thing that you should learn from this particular lab is retrosynthesis or back synthesis. You should understand which is the vulnerable double bond that you can take off. You can break off these double bonds, but none of these because they are part of your aromatic structure. You cannot just break out the double bonds for benzene. So we will learn about the retrosynthesis and the back synthesis very soon in this particular experiment. But I want you to pay attention that this is your original ketone on where we have substituted our two aldehydes. Because we will get more than 10 carbon long chain, we are going to get a material which will be insoluble in water. Because it is insoluble in the aqueous solution of sodium hydroxide, ethanol, and so on, this will crash out as a solid. So you should know why will you be able to isolate your product. Another thing, because of its high conjugation, this product will be a colored product. So the more number of pi electrons are there, the more number of pi electrons that can delocalize from one end to the other, the more conjugation there is, the more colored or deeper color that material gets. Now, some of the things that you must learn from this particular lab experiment is how to generate enolates. So you will be given different kinds of carbonyl structures, and you will be asked to draw out or figure out the enolates from those carbonyl structures. Remember, enolates are your nucleophiles. You get them from abstracting out a alpha hydrogen. Why the alpha hydrogen? So if you look at this particular part of the screen, the hydrogens of your alpha have a pKa value almost about 20. It is very close to those of alcohols. But if you look at the pK value of the aldehyde's hydrogen, it is quite basic. So when you have sodium hydroxide, the base, will it abstract the base or will it abstract the acid? It will abstract the acidic hydrogen and not the basic aldehyde. So this is one of the mistakes that most of the students do. They forget that the hydrogen of the aldehyde is basic. If you do not remember the pK values, that's completely fine as well. What you can remember is the relationship of carbonyls. When you have a carbonyl carbon, it is electrophilic. It is electron poor. Whereas oxygen is electron rich because of its electronegativity. So if you pay or if you plant formal charges on these carbons, we see that a positive charge appears on the carbonyl carbon and a negative charge appears on the oxygen. So following this trend of plus minuses, the hydrogen next to your carbonyl carbon is a basic hydrogen. It is not a positive kind of a hydrogen. On the other hand, if I look at the hydrogen of alpha hydrogen, that is, So carbonyl carbon gets the positive charge, oxygen gets the negative charge. The carbon next to the electrophilic carbon gets a negative charge because of the opposites. And the hydrogens on this carbon will get what? A positive charge, which is indicating acidic nature of this hydrogen also. So this is just a temporary clue that you can use for figuring out where are your acidic hydrogens. Between a ketone and an aldehyde, who will be acting as your electrophile? The aldehydes are better electrophiles than ketones. So when you generate a enolate, it would rather attack the carbonyl carbon of an aldehyde. It can attack the carbonyl carbon of a ketone also, but it would do that slowly. The reason are electronic and steric effects. If you look at this particular structure, the hydrogen molecule is smaller in size. So when the incoming nucleophile approaches, it only has to deal with a small bulk here. Whereas if the nucleophile approaches the ketone, it will be facing steric hindrance from this bulk as well as this bulk. And so steric factors make this carbonyl carbon very electrophilic because the nucleophile can approach easily. Also, if you look at the ketone, the alkyls are electron releasing groups, making this carbon electron rich. If this carbon is electron rich, it will not be reactive. It will not be ready to receive the nucleophile. So you do not want your carbonyl carbon to be electron rich. You definitely want it to be electron poor.